So in this video, we're going to go over the second part of the fundamental theorem of calculus. I know fundamental theorem of calculus is sort of like mathematical and like super complex, but it's actually not. It's actually pretty simple. So let's get right into it. So here we have that a more simple way of finding the area under the curve. Area under the curve is a definite integral, right? So we're going to discuss here what the difference between an indefinite integral to a definite integral is, right? But before that, to be able to apply the second part of the fundamental theorem of calculus, we need to go ahead and check two things. First, that our function is continuous over the closed interval from a to b, and that it's differentiable on the open interval from a to b, right? So those are two conditions that seem to come up a lot in calculus when it comes to theorems, right? And what part 2 tells us is that we're going to find the integration from a to b, which is our lower bound and upper bound of our function. We're going to find the area under the curve of our function from a to b, and it's going to be given by subtracting the difference between when you plug in b into your integration and when you plug in a into your integration. And if that's a little rough right now to make sense, no worries. We're going to go ahead and do examples on it to see how simple it is to just go over this. So let's go ahead and find the definite integral here in example 1 from 0 to 4 of x squared. So here what we need to do is we need to first integrate, right? So to go from our integration to integrate, we're just going to go ahead and integrate this x squared, which the integration is x to the third over 3, and we no longer do plus c, right? So that's one of the biggest differences, right? That we no longer, whenever we talk about definite integrals, right, we no longer need to worry about our plus c. So we no longer do this. We now go ahead and just put this little bracket. We integrate, so we get x cubed over 3. We put our bracket, and then we put our bounds, right, which are from 0 to 4. So we put those right here, from 0 to 4, right? So once we do that, we're ready to apply the part 2 of the fundamental theorem of calculus, which means that I'm just going to plug in, 4 into my equation. That's my f of b, right? And I'm going to plug in 0 into my equation, and I'm going to go ahead and subtract those two, right? So I'm going to go ahead and give myself a little more space and have, when I'm plugging in 4, which is my b, I just plug in 4, so I get 4 cubed over 3, and then I subtract it to whatever I get when I plug in 0, right? So we can see this right here, this part, we can see it as f of b minus f of a, right? The integration is x cubed over 3, and I'm plugging in b into this one, and I'm plugging in a into this one, right? So then this answer right here has a 0 in it, so it's going to go away. But this answer here is 4 cubed over 3, which is going to give me a total of 64 over 3, right? So that's much more simple than having to do the area as a limit, right? So this stuff is going to be much faster than having to do an area as a limit, and it's much more efficient. So just how we learned derivative rules, these are our integral rules that we can apply instead of the limits. So now we can apply this for integrals of polynomials as well as trigonometric functions. So let's go ahead and see how the area of sine of theta d theta is from 0 to pi over 2, right? So what we did here was, let me draw you guys a little sketch so we can kind of see what's going on. The sine function looks like this, something like that, right? Its period, normal period is 2 pi, so right here it's pi. So this right here is pi over 2. So we're actually trying to find this area, right? We're trying to find that little area there, which is the area under the curve and the x-axis from 0 to pi over 2. So our endpoints from 0 to pi over 2 are these, 0 and pi over 2. So we're trying to find the area between those 2 points, right, under that curve, under the curve. So, which is in yellow. So if I go do that, all I have to do is I need to integrate my function. So when I integrate sine of x, I get negative cosine of x, right? I get negative cosine of theta, well, of x or theta, doesn't matter. And now I'm going to go ahead and just put my little bracket from a to b, from 0 to pi over 2, and I'm just going to apply the second part of the fundamental theorem of calculus, which tells me just to plug in my a and my b. So I have a negative cosine, so I'm going to go ahead and find negative cosine of theta minus, I have a negative function, so I can just put a negative cosine of theta here. So this is a little different. I'm going to input my b here. I'm going to input my a here. So you guys can see you're just using your antiderivative or your integration, and then inputting your b and inputting your a, right? So how we're going to do this is that first these two negatives are going to turn into a positive, and then the cosine of pi over 2, right? If you guys have any questions on that, let's just draw a quick unit circle right here, right? Where pi over 2 is right here, right? And the coordinates of that point are 0, 1. And the cosine of pi over 2 is going to be 0. It's going to be the x, right? And then it's going to be negative 0 or 0, doesn't matter. Plus, what is the cosine of 0? Well, now we have to look at 0, which is over here. This is pi over 2. This right here is going to be 0. And the coordinates of 0 are going to be 1, 0. So it's going to be positive 1. So my answer is going to be a total of 0 plus 1, or just 1, right? So we're just kind of taking indefinite integrals to a different level by just doing our indefinite integral. We're going to compute our integration, and then right after we're just going to input our intervals, right? Our a and b. That's all we're going to do. So these are just a matter of plugging in. So I chose easy functions with easy plugins, so we wouldn't spend too much time just like multiplying and adding fractions and numbers. And that's not the point of this. The point is to think about what a definite integral is, which means that I'm bounding a certain area on a certain interval, which is what I showed you guys right here in the picture of the sine. So here, for example 2, we're going to run into a interesting situation, right? Because so far we have gotten 64 over 3, and we have gotten 1, right? So these two answers actually have something in common that the answer in example 2 is not going to have. And you guys are going to see, and then you'll tell me what it is, right? So here I'm finding the definite integral from 0 to 2 of x squared minus 2. So I gave you guys the graph here, and we're finding the area from 0 to 2 under the curve of this function, right? So that means that I'm actually going to find out this area, because this is under the curve and the x-axis, and then I'm also going to find out whatever this area is, whatever that is. Okay, so I'm finding out that area right there, right? Because from 0 to 2, that is my function, right? This is my function, and then I'm also bounding it with the x-axis. So the area that corresponds under the curve from 0 to 2 of x squared minus 2 is that area right there in yellow. So when I find that, I'm going to go ahead and just first find my indefinite integral. I just find my integral of x squared minus 2, which the integral of x squared is just, I add 1 and I divide by that exponent, which is going to be x cubed over 3. All right, I put a minus, and what is the integral of 2? It's going to be 2x, right? And I don't put a plus c because I'm doing a definite integral. I just go ahead and go from 0 to 2. I put my bracket, then I put my interval, my a and b. And then now I just go ahead and plug in. I'm trying to do my f of b minus my f of a, right? So here I'm going to have my f of b. Here I'm going to have my f of a. So here I'm going to have a number to the third minus 2. And then here I'm going to have a number to the third over 3 minus 2 times that number, right? So I'm going to plug in my b first, right? This is my f of b, so I'm plugging in 2 here first, and then I'm plugging in my 0, so I'm going to plug in my 0 here, right? So this is going to give me 2 cubed. So 2 cubed is going to be 8 over 3. And this right here is going to be minus 4. So I get 8 over 3 minus 4 for the f of b. And then you get 0 cubed over 3. Well, that's 0. And then 2 times 0 is just 0. So this whole side kind of just goes away. It just kind of gives me 0. So no big deal about that, right? I'm just going to focus on this 8 over 3 minus 4. And you can calculate that in your calculator. Or you can go ahead and do it, which is just 4 over 1, right? This is 4 over 1. So I'm just going to multiply. I'm going to get common denominators. So I need to multiply this by 3 and multiply this by 3. So I'm actually getting 8 over 3 minus 12 over 3, which gives me negative 4 over 3, right? So what makes this answer different from the other two answers that we've gotten? Well, the fact that this answer, this definite integral, is a negative answer. But what does it mean to have a negative area? Is that possible? And here's the deal, that the area isn't negative. What this is telling you is how your area is being distributed, right? And by being distributed, I mean, then that leads us to our question here. what is the meaning of a negative integral or a negative area, right? The point is that since most of the area, if you guys see, let's call this chunk A and chunk B, right? If you guys can see, the area A is bigger than area B. But what about area A makes it different from area B? And that just means where it is in relative to the x-axis, right? So if the area is below x-axis, right? So below x-axis, it is going to be negative, right? If it's above, it is going to be positive, right? So since we have a negative answer for our integral, that just means that most of our area or more of our area is under the x-axis than over the x-axis. And this is going to take a whole different meaning when we actually apply our integration to finding other things that we can do with integration. But for right now, the meaning of a negative integral is going to mean that most of the function is under the x-axis, and that's where we're going to take it, right? So in this case, right? So in this case, in example B, we can see that all the area that we have is over the x-axis. All right? And that's about it for now. We're going to go ahead and do some practice problems on the second part of the fundamental theorem of calculus.